Hello, my name is Jialiang Zhang. Today I will be presenting our work, Software-Defined Address Mapping, ASPLOS on 3D Memory. I will start with executive summary. To fully exploit the parallelism in emerging memory devices, data placement must be at fine-grained and vary with different access patterns. Existing hardware-based mechanisms can achieve fine-grained control of data placement, but cannot support multi-access patterns. Software-only methods can support multiple access patterns, but can only provide control mechanism at coarse-grained granularity. We propose STEM, which enables user program to obtain a direct control of the low-level memory hardware in a more intelligent and fine-grained manner. Evaluation on data-intensive benchmarks demonstrate 1.8x speed up on CPU and 2.6x near memory accelerators, compared to a baseline system that uses a fixed address mapping. We believe STM is an essential step towards software-defined memory, which allows user program to obtain direct control of the low-level memory hardware in a more intelligent and fine-grained manner. Modern computer systems tends to have more and more memory-level parallelism. For example, in the past 10 years, the number of DDR memory channels increased from 4 to 8. To further increase the memory-level parallelism, 3D stacking memory provides significantly higher peak memory bandwidth by employing new parallel memory architecture that vertically stack multiple DRAM dies using TSV technology. For example, HBM stack consists of multiple DRAM layers organized hierarchically, where each layer is further divided into 2 channels, and each memory channel consists of multiple memory banks. Altogether, a single socket can integrate up to 4 HBM stacks that provide 64 independent channels. Now the problem is how to fully utilize the abundant memory level parallelism in the modern computer systems. Before discussing the challenge of exploiting memory level parallelism, let's first see how data is placed in the physical memory hierarchy across channel banks rows is achieved via 2 steps. The first step is VA to PA translation, and the second step is the physical to hardware address mapping. The VA to PA translation maps large per process virtual address space to a single one-dimensional linear physical address space shared by all processes. Such translation is managed by the OS kernel. In contrast, the PA to HA mapping further transforms the 1D linear physical address space into an internal multi-dimensional hierarchy structure of channels, pseudo-channels, rank, bank groups, bank, and rows. The PA to HA mapping is typically managed by the hardware, for example, memory controller. In this slide, we are going to see why the data placement is very critical to fully utilize MLP. The MLP utilization is determined by access pattern, which is a sequence of virtual memory address, and also the data layout in the memory address, which is the data structure, the layout in the VA space after two levels of address translation. This 2 example on the right shows one possible data layout and 2 access paths. On the top one, we can see the access pattern. The access pattern of stride equals to 1 case. We can see all the access goes to different channel, which means it can fully utilize the memory level parallelism. In contrast, for the stride of 8 case, there are severe channel conflict that all the memory access are consolidated into one channel. On the contrary, another layout may only work for the straddle of 8 case. Let's see the example on the top. There are severe channel conflict for the pattern's stride equals to 1. And for the stride equals to 8, all the memory access goes to different memory channel, which leads to better channel level parallelism utilization. From this example, we know that to improve the memory bandwidth utilization, we need to control the data layout in the memory device via 2 levels of address translation according to the access pattern in the data structure. Let's take a closer look at the 2 kinds of memory translation. VA to PA translation can be controlled by software but only provide control mechanism at coarse-grained granularity due to the limitation of paging. PA to HA method can achieve fine-grained control of data placement in physical memory, but it is not programmable. Hence, to improve the MLP utilization, we propose to preserve the high-level information during the VA to PA translation, and use those information to guide the PA to HA translation to achieve fine-grained control that is guided by the software. Here we present our SDM technique. SDM is a collaborative software-hardware technique that improves PA to HA address mapping, but does not need any modification to existing VA to PA translation. First, we collect the access pattern information from the program, either provided by the programmer or ML-based approach. Then we cluster similar access patterns that can use the same address mapping for good MLP utilization. OS configs large chunks of memory for the aggregate allocations reached by a variable. Data with the same access pattern address mapping will be placed continuously in the physical memory, so that SDM can manage the low-level data placement policy at coarse granularity, but the data placement itself is still at the cache line granularity. The key to achieve efficient SDM is the coarse-grained chunk-based address mapping. In chunk-based address mapping, we map a pool of data with the same or similar access patterns to chunks during the allocation of virtual pages and physical frames. Each chunk consists of contiguous physical pages containing data with the same access pattern. The kernel maintains a chunk mapping table, aka CMT, that stores address mapping information for each chunk. At runtime, the memory controller looks up the address mapping based on the PA of chunks. Then it calculates the HA based on the PA and the address mapping. Finally, it uses the HA to place cache blocks across channel banks rows in 3D memory. Now, let's take a closer look at the implementation detail, including the architectural support, software support, and the machine learning system to identify the address mapping. Let's start from the architectural support. To implement SDM, the required hardware modifications to the existing processor are relatively minor. There's no need to modify the architecture of the CPU cores, for example, ISA, TLV, or page worker. The only modification is to add a dedicated hardware component in the memory controller. An address mapping unit, aka AMU, contains a simple crossbar to support arbitrary address mapping, and on-chip SRAM to store the address mapping information configured by the physical page allocator. For each DRAM access, the MSB of PA is used to index the CMT to find the corresponding entry for the address mapping. Then the AMU will map the LSB from the PA to HA. Now let's take a look at the software support. The chunk-based address mapping requires modest modification to the system software for both virtual memory and physical frame allocation. Rather than using a single allocator, we separate the memory based on the address mapping. Then we can have an allocator for each mapping and provide a way to move memory between mappings. For each memory allocation call, the virtual memory allocator allocates the VA on the heap corresponding to the address mapping provided by the application. For each page fault, the physical frame allocator will retrieve the address mapping from the heap based on the virtual page number and allocate physical frame based on the address mapping and configure the chunk management unit. To absolve the programmer's responsibility of finding access pattern information to select address mapping, in addition to providing the interface to direct select the address mapping, we develop a method that can automatically find the variable that contributes most to the external memory access. Then we apply machine learning to identify the access patterns of these major variables and further clusters the access patterns into a reducer size to reduce the storage overhead of the metadata. Depends on the software and hardware constraint. We provide additional flexibility of making quality time trade-off for selecting address mapping. For example, user can choose to have a fast runtime using k-means in which clustering quality is likely constrained. Alternatively, user can choose to have slow runtime and using the deep learning assisted k-means for higher quality. To accurately capture the detailed HBM-specific behaviors and the comprehensive interactions between OS and hardware, we evaluate our design on an open-source full-system FPGA prototyping platform. with integrated HBM devices and the full OS stack. Our baseline system comprises a boom RISC-V processor and a shared memory interface for near-memory accelerators on the Alpha Data FPGA board, equipped with a Silex VU37P FPGA that has an in-package 8 GB HBM2 memory. It supports Linux, allowing us to evaluate our modification to the functions in the glibc and Linux. In the experiments to perform comprehensive evaluation, we select a broad set of benchmarks, including synthetic memory access benchmark, standard benchmarks, as well as representative emerging data-intensive benchmarks in 3 important domains, which can cover large-scale graph processing, in-memory data analytics, machine learning, and information retrieval. In addition to the evaluation CPU, we also evaluate the performance gain of offloading data-intensive workloads to hardware accelerators, which becomes increasingly important in data center and HPC. Due to the limit of time, here we only discuss the result for standard benchmark and the representative emerging data-intensive benchmarks. BS plus DM represents a single fixed address mapping. BS plus BSM represents a single address mapping for all application identified profiling. BS plus HM represents the advanced address mapping based on the hashing function. SDM plus BSM represents that for each process, it uses a single address mapping, choosing based on the bit flip rate. The SDM plus BSM plus ML represent that selecting the optimal address mapping for each individual variable within the application using the k-means-based approach. Similar to the ML-based approach, the SDM plus BSM plus DL select the optimal address mapping using the deburning-assisted k-means. We can see that the SDM plus BSM plus DL can achieve 1.3x and 1.4x speed up over the BS plus DM for 4 clusters and the 32 clusters respectively. Comparing the ML and the DL method, we can see that DL-assisted k-means achieves consistently better performance, insensitive to the number of clusters chosen for each application. However, the ML works well for applications with a smaller number of major variables such as Perl and MCF. For applications with a large number of variables such as like OMNetPP and A star, the ML has nearly no performance gain. But the DL can deliver a speed up of like up to 1.3 and 1.2 times. For data-intensive benchmarks, the BS plus HM achieves similar speedup as that observed in standard benchmarks. In comparison, the SDM plus BSM plus DL have higher speedup on data-intensive benchmarks than the standard benchmarks, as they have more memory access. The results are consistent with our expectation that emerging data-intensive application would benefit more from our proposed technique. To conclude my talk, in this work, we propose software-defined address mapping, which is a new system mechanism that enables user program to obtain direct control of the low-level memory hardware in a more intelligent and fine-grained manner. As a case study, we have applied SDM to 3D stacking memory to better exploit CLP by controlling the address mapping, adapted to the data access pattern to different data structures across application at runtime. We apply machine learning for system optimization to further reduce the overhead of SDM and improve its performance. We believe SDM is an essential step towards software-defined memory. Thank you.